Hi, everyone. Welcome to our webinar with Prior Labs. Really excited to have you all listening. So thank you for joining in. I'm good. We're going to introduce today Prior Labs, Frank, who is the CEO of Prior Labs, and then leave a few minutes for questions at the end to Q&A, and also feel free to ask questions in the chat so we'll be able to see them. We'll be structuring the webinar today into three parts. One, quick introduction, and then the first section about Prior Labs, its journey, the second section on the performance and benchmarks, and the third on a few use cases. So Frank will be walking you through these sections. So again, please don't be shy, and please feel free to ask questions, whether you have used TabPFN or not. All questions are valid. So without further ado, really excited to introduce to you Prior Labs. Prior Labs, which is one of the top tech companies in Europe, specialized in foundation models for spreadsheets and databases. It's raised €9 million in pre-seed funding, led by Balderton Capital, alongside XTX Ventures, Atlantic Labs, and Gallion Exé, so top seed funds in Europe and also in France, and top angel investors from Hugging Face and a lot of other exciting tech companies. Today, the focus will be on the release of TabPFN 2.5 and the launch, and so we'll be walking you through more around that. Frank, the CEO of Prior Labs, has a great background in computer science, a doctor of philosophy at the University of British Columbia, followed by the University of Freiburg. So the Prior Labs team is really a combination of the top operational talent and the top technical talents in Europe today. Frank, I'll leave it on to you to say a few words of introduction, and then we can jump right into TabPFN 2.5 and the new releases.
Yeah, thank you all for joining. It's very exciting to be here and to be speaking about TabPFN 2.5 for the first time. It's been a really exciting journey so far. We founded the company close to a year ago. And before that, I actually was a professor for 10 years, focusing on tabular data, on AutoML, on really democratizing machine learning and making it much easier for everyone, including non-experts, to actually use state-of-the-art machine learning. And that's a journey that we've been accelerating with Prior Labs. And yeah, with TabPFN 2.5 are the closest to that anyone has come, I believe.
Amazing. So this is the first webinar talking about TabPFN 2.5. So a few numbers. It's crossed 2 million downloads. It's been cited in 400 papers in the past 10 months. And so this is just to tell you a bit about the scale. It scales to 50,000 rows and 2,000 features. So my first question to you, Frank, is what does this unlock for practitioners that wasn't possible before?
Well, I mean, really, it's unlocks just much better performance. So for the sizes, the size constraint that TabPFN v2 actually enabled, it's dramatically better at that. But also, it now can scale to just a lot more data. Actually, we just recently realized it's state-of-the-art for 100,000 data points and 2,000 features. So yeah, if you have between 10,000 and 100,000 data points, and a lot of people do have data sets in that range, then yeah, all of a sudden now this is actually applicable. And previously people tried to apply to that and then subsample the data to 10,000 data points, and that just didn't really do very well. And now, yeah, you can just natively in a forward pass in seconds actually get state-of-the-art predictions. Rather than going through complex AutoML workloads that take over the weekend or something like that. You can now do this in seconds, and you can then actually iterate so much faster and focus on the stuff that domain scientists are very good at, getting the right features, getting the context, problem formulation, etc. That is something that in traditional AutoML frameworks just totally was left on the wayside, and that is something that we're actually enabling now, putting the domain expert back into the picture and then giving them the tools to iterate really quickly on data science.
Perfect, really exciting. And yeah, I guess as a brief highlight to that, and I forgot to introduce myself, but very, very briefly. So I've been doing data science in the past, and today I'm a partner at Gallion Exé, which is a leading seed fund in France. And so I think it'll be great to talk about some of these data science benchmarks, which we'll talk about later. But just to resonate on the 3 points you mentioned, so higher data set size limit, fast inference, improved state-of-the-art performance, and delivery of a bunch of things that data science can do and that we've all been doing over the years. So spending hours on classification, regression, forecasting, anomaly detection. So these are all some of the things that, whether it's data scientists listening to us or CTOs, can be using TabPFN to simplify their work. I guess the second question to you is, TabPFN started out as a research breakthrough and now has become the go-to foundation model for tabular data. Where are you taking this? And could you tell us a little bit more about synthetic data and how you train TabPFN on synthetic data?
Yeah, maybe I'll just talk a little bit about the background first. So I think actually to catch everyone up, I should mention in the first place, what is tabular prediction? And then I can talk about the research breakthroughs, right, and where the synthetic data comes in. But so tabular prediction is really this age-old problem that sort of for like 50 years has been building really the core of machine learning in industry. There is all kinds of problems that you can formulate as a tabular prediction problem. It's sort of always you have this, you have rows, each data point is a row, and you have columns, and each column is sort of a feature that describes the data point. In this case here, a data point is a customer, and from these features you want to predict, will this customer actually buy a certain type of insurance or not? But you can formulate it like this, any type of problems. For example, will customers churn, or like what disease does a patient have, which product will a customer buy, will someone pay back a loan or not, etc., etc. So it's these age-old problems that we've been using, or that the community has been using, gradient boosted decision trees, and before that sort of random forests and SVMs and linear regression, etc. And this is a problem that really where we've been stuck in these methods, traditional methods implemented in scikit-learn, that can't do all of the things that we want them to do with modern machine learning, modern deep learning frameworks. So for example, we don't have any understanding of free text. We don't have any understanding of like missing values, and then something like gradient boosting. We have no semantic problem understanding, like what is this churn thing? What might this relate on like previous context, the contextual knowledge of LLMs is just totally not in these models. You don't have transfer across different data sets. You have poor auto distribution predictions. Like if you have only a small number of data points, and typical gradient boosting methods just overfit a lot. You can't integrate these trees properly with LLMs. You can't backprop gradients through that. You can't search in there. You don't have embeddings of your data. You can't learn in multiple tables, and you just always manually take your relational database and make a machine learning problem out of that, and then fit your gradient boosting on that. Rather, you want something that actually operates on multiple tables at once. You can't integrate domain knowledge into gradient boosting properly. You can't add data or remove data really easily. So there's all these problems that traditional gradient boosting methods don't solve. And on top of things, now actually gradient boosting is not giving you the best performance anymore, but these new deep learning methods. So what the deep learning revolution is offering is to fix all of these issues. We have not solved all of them quite yet. We're on our way. Many of them we have solved, in particular the cross data set reasoning we're particularly good at. But based on top of what we have, we can do all of these now. But more generally, these foundation models have transformed text and images. We know that LLMs dominate our AI world. Images are dominated by foundation models, but databases, spreadsheets, CSVs, time series, all this tabular data is actually just has been this gaping hole, and that's where Paralab sits. And the promise of these foundation models for tabular data is that we have one model that just solves them all. So if you have many different types of questions, like what if is this patient at risk of deterioration, or what's the transaction that this person has made, or which product will the person buy, etc. Your traditional world would say, well, we just take this data point, we look at this data set that was built particularly for this workflow, and then that's a data science problem to actually fit a model on these types of tasks. And then we train a model and we solve a predictive problem. And this data science task might take you, if you're really good, a couple of hours, typically more days to weeks, or maybe months until this data science task is solved. And then you have these separate models that don't talk to each other. You don't have positive transfer. And in contrast to that, a foundation model would just take all this data and put it into one big pre-trained foundation model, train once on many different data sets, and then have a model where you can just, in a forward pass, make queries. And this model you could still fine-tune to the data in a particular application domain, just like you can download a Llama and fine-tune it to your text data. But you don't have to. You can actually work with very little data here. And that is the promise of foundation models that has revolutionized text and images and is now revolutionizing tabular data as well. How does this work? Where does the synthetic data come from? So that is basically this one slide here is sort of TabPFN in a nutshell. Left is the training, and on the right is what we actually do at inference time when we get a real data set. So at training time, we have these data sets. Again, this X train, Y train, X test. These are the features, training data points, and then test data points where we don't know the Y test. In the generated data that we generate from scratch, we have the full data set with the Y test. Take the Y test out, take the rest here, feed it into a TabPFN that makes some predictions. And initially, before we have trained, it makes some bad predictions. And then we see how likely is this Y test under this predictive distribution, and we backprop through that. So for one data set that we sample, we do one backprop. Not like in traditional deep learning, where for one data point you do a backprop, but here for one data set, we do a backprop. And then we generate a new data set, we do predictions, we backprop the error, and we do that over and over again, like hundreds of millions of times. And that at the end, we actually have a parameters of this model that allow the TabPFN to make good predictions for whether Y test predictive distribution actually very much resembles the true Y test. And that is a time when we stop the training, and when we have the trained TabPFN, then you take a real data set. This is the first time that a real data set enters the stage. And here you truly don't know the Y test. You pass it in one forward pass, you get this predictive distribution done. And this forward pass, is very easy, very simple. You could just actually put this, like write this out in Onyx, put it on a sensor, and then you have on that sensor, you have a machine learning algorithm that's running. It's not a classifier, but it's a machine learning algorithm that for new data can actually learn a new type of classifier on the fly in seconds. And I love AutoML. I sort of founded the field, but and we did write AutoScaLearn, which wraps around scikit-learn and does Bayesian optimization and meta learning and builds ensembles and whatnot. And people didn't really like it that much because it was this complex workflow. It's really slow, it's complicated, it has all kinds of dependencies. This is a forward pass in a neural network, and it can't be more commodity like this than this. And on top of that, it's actually better in seconds than this was in days. So that is a promise of TabPFN, that it really gives you all the stuff that AutoML wanted to offer you, but actually gives it to you sort of at your fingertips. While you write the next line of code, you should get the predictions of your previous prediction. That is the hope.
Yeah.
The synthetic data, it comes from structural causal models. So we built a Bayesian posterior over all possible structural causal models in order to do causal inference in a forward pass. But maybe I won't go into too much detail there.
Yeah, awesome. And we already have one question from the audience, which we'll answer later. I'm also sharing the technical report for Paralabs. For all those who haven't read it yet, can follow through the technical report at the bottom of the page. And this, I think, is a really interesting transition before we jump into the use cases of financial and health, etc., that Frank shared before, onto TabPFN 2.5, matching the accuracy of AutoGluon 1.4, tuned for 4 hours, and outperforming XJ Boost and Cat Boost. And so my question to you, Frank, is, how can you walk us through what that means and how you're computing against the best AutoML systems in terms of numbers and showing us the results?
Sure. Yeah, so first, TabPFN now handles larger data sets. And actually, as we really realize now, it handles up to 100,000 rows and 2,000 features, which sort of we use this Tabular benchmark that has that data range. So we use all of it now. Previously, we used to use this like really small subset that was limited to like 10,000 data points. Now we use all of it, and in one forward pass, that's the blue here, is if you just do one forward pass, and the green is then if you do assembling on top of that. But so in one forward pass, TabPFN and real TabPFN, which are both instantiations of our new model, actually in a forward pass do better than all the other models do just in a single without tuning. And the orange one is with tuning, so tuning for 4 hours. And even the forward pass of TabPFN is even better than tuning of any of the other methods, including this new quite cool version of an MLP by actually Leo, who is our first joiner. But then also other, like in particular, the gradient boosting methods like UBM Cat Boost, XG Boost here, you do see that their default performance in blue is actually quite weak. Tuning really does help you quite a bit in terms of XG Boost, but still doesn't get you anywhere close to the default performance of TabPFN. And then if you do look at smaller tasks, like where TabPFN v2 used to work, we even have clearer dominance of the state of the art. And here you have the fact that TabPFN in a forward pass is actually better than an ensemble of all the previous methods taken together, optimized for 4 hours. And that's what AutoGluon does. That's it's sort of the continuation of AutoScaLearn. And that is the highly complex method. Actually, that previous ensemble already includes TabPFN v2. So in this plot here, this is a TabPFN v2 compatible that allows us to actually compare TabPFN v2. How big was the jump from there to 2.5? And we can see it is quite dramatic. So actually, 2.5 in a forward pass again is better than TabPFN2 ensemble, then optimized for 4 hours. So very substantial jump in performance and very strong dominance of the tree-based methods.
Yeah, I think this is really interesting, and how you're competing against the best AutoML system. So Frank, you've been in the field for years and years, and I remember spending countless hours on not only data cleaning, but then having to find the best model and having to then perform compare XG Boost versus other models, and that test and learn process, which is kind of endless, and then finally interpret the results. So I think this is hugely time saving. And so this brings us to the real world. And so beyond public benchmarks that you've tested on internal data sets across healthcare, finance, insurance, manufacturing, what did you learn? And what makes your internal benchmark different from the Tabular benchmark?
Yeah, so actually in this internal benchmark, it is not that different in terms of the benchmarking strategy. It's just different in terms of the data that goes in there. So it has maybe a bit less toy data sets, the typical data sets that are on OpenML, etc. They've been on there for like 30 years and are maybe not the most up-to-date data sets. So in our internal benchmark, we have data from customers and data from particular markets, from the industry, from finance, from medical, etc. So we collected this benchmark where if we make progress on that, we believe it really reflects progress in the community quite a bit better than public benchmarks. For example, for regression, Tabular, for really large data sets, there's like 7 data sets. And yeah, we just have many more data sets that are relevant. And what we did here is to actually look at the normalized accuracy and normalized ROC AUC. That's a very similar metrics as you would look at in Tabular, and very similar results. So we would tune the different gradient boosting methods and see them, like when you tune them, they do get better, but no comparison to TabPFN, both in classification and regression. Here, and we use, so in our Nature paper, we actually compared the default of CutBoost against the default of TabPFN, and then the tuned version of CutBoost to the tuned version of TabPFN. By now, we actually went to like not a tuned version of TabPFN, just a default version, because the plots more or less look the same as here. So when you tune, some of these data sets actually get better for CutBoost a little bit, but most of them, just the non-tuned TabPFN still clearly dominates the tuned CutBoost. And this is all highly statistically significant for classification, but then also for regression, we made quite substantial advances. The TabPFN-V2 was not quite as strong on regression, and the new 2.5 is quite a bit stronger on regression. So you see again, very similar. The default here clearly dominates the tuned methods. And
no, that's really interesting. And I think that'll tie up well with some of the questions from the audience. And once again, encourage everyone to check out the technical report from Prior Labs posted in the chat, comparing more the ROC curves that Frank described and the differences in accuracy. And just to highlight what Frank described, having read the paper, Tabular, it contains data sets with up to 100,000 training data points. And TabPFN 2.5 has a 100% win rate against default XGBoost models at a really good win rate. So 87% win rate on larger data sets.
So if you actually look at this slide, I just put this in, Margaux. I didn't tell you before. But okay. This is a very detailed plot from the paper that for any of these methods compares it against any of these methods. So that's the same methods here and there. The diagonal, because of that, is 0.5. But you see at the top, there is a real TabPFN. Actually, I didn't mention what real TabPFN is. That's an iteration on TabPFN that tunes a little bit on a broad set of a real data set that is disclosed, which types of data sets. They don't overlap with the evaluation benchmarks here. But what I did want to say is TabPFN-V2 in the default actually got this 69% win rate against the default CutBoost. Default XGBoost, and the top method now really just has 100% against XGBoost. So all of these, I actually don't know how many, but like definitely many dozens of data sets, it is better. So this is that's where we want to be.
It's a very nice slide.
Very easy for practitioners. You don't need to think anymore. Just use TabPFN. You don't need to go tune XGBoost and so on. That's where we want to be. And of course, sometimes ensembling still helps a little bit, but with the steep gradient of foundation models, I think we will see this more and more, that the smaller the data set, the less you need to think, and you just use a foundation model.
Amazing. And we're going to jump into the use cases because we do want to leave 10 minutes for Q&A at the end, and real world use cases. So you've documented 100 plus published applications, from cancer diagnosis to predictive maintenance to wildfire prediction. Could you share some examples and walk us through why TabPFN worked where traditional methods might have struggled?
So it was really nice to see like the community adoption of TabPFN. When we published the V2 in Nature. Since then, there's been like over 400 citations in published scientific articles, and over 100 of these are actually about use cases of TabPFN, using it for X, Y, Z. And actually over half of those come from the medical domain. This is very fascinating. There's a lot of exciting uses there where TabPFN is actually really used to save lives. It's in actual lab tests in the hospitals in the UK, and it's being used for so many different applications. But let me actually. Oh, I thought I have a slide on this. I don't. But so we have we have applications with Oxford Cancer, where analytics where we're looking at sort of these proteomic markers in order to categorize different lung diseases based on sort of liquid biopsy. They have a really cool pipeline to get these proteomic markers, and it leads to all this really rich data. And this really rich data allows you to actually classify the different lung diseases. And okay, I can go to the slide. This is just one of the many different types of applications. We also have we also collaborate with Hitachi in a completely different field. This is in the case of Hitachi, it's actually predictive maintenance of railroad tracks, where there's all kinds of different issues that can happen to railroad tracks. And you don't just want to go and say, well, like every 5 years I'm going to change my tracks, but you want to actually look at, well, how good are the tracks? How heavily have they been used? What's their what are their characteristics? Are there any anomalies? What's the probability that something might happen? And you want to fix the tracks that are most at risk of something happening, and maybe leave the tracks alone that are perfectly fine, and focus your resources on the important ones. So these are two use cases that we can publicly talk about, but we have so many different ones. For example, one that is just very well known in the public domain is sort of credit risk, deciding whether to give a loan or not to give a loan. And sometimes the data sets are not actually that large, and XGBoost and CutBoost and so on can overfit a lot. What we have seen in terms of the ROC curves is that the training performance of CutBoost and all the different gradient boosting methods is actually very high. You sort of fooled into thinking, oh yeah, this is going to work great. And then when you look at test set performance that withheld data, it's actually very bad. And TabPFN has learned not to overfit. That's its gradient signal, trained over hundreds of millions of data sets. It's been trained to do well on the held out test set split of these training data sets that are synthetically generated. And so when you actually look at the new data set, if you look at the performance of on the training set and on the test set of that new real data set, then the training set performance is actually, it's okay, but the test set performance is almost the same. Whereas for the gradient boosting, the training performance is amazing, and then the test set performance is really bad. So this overfitting is precisely what misleads you, and there's a whole lot less overfitting with TabPFN because it's trained not to do that.
Yeah, that's really interesting, and I think for all the data scientists in the chat can relate to overfitting problems. So again, in the technical report paper, you have a little bit more about not just the accuracy and the F1 scores, but more about this overfitting piece versus XGBoost, and also the larger processing capabilities. So TabPFN 2.5 being up to 2.3 times faster, thanks to optimized pre-processing. So I think that's really interesting. I guess to get practical for all those listening, two final questions. You announced some big commercial partnerships. What are they now that they are public? And secondly, when should someone reach out to use TabPFN 2.5? How can someone try it out for all those who might not be familiar with TabPFN?
Yeah, actually, so the these two partnerships were the ones I just talked about. So Hitachi, where we're partnering with, they're I knew I have a slide. Sorry. Yeah. So they're this a big company with $150 billion market cap. The use case there is predictive maintenance of these critical railway infrastructure. And it's not just one type of anomalies that they want to detect, but really, diverse technical environments, diverse technical problems, diverse issues with the railroads. They want to figure out, and it's not just one model, but it's many different models for many different types of problems and environments and so on, based on different features. And so incredibly excited. We just announced this today. And the other one was this Oxford Cancer Analytics, where they have a proteomic data based on liquid biopsies in order to really strengthen the diagnostic capabilities and guide better treatment decisions and actually help patients survive better and have better treatments for these lung diseases. And the strategic value here is, of course, it's really complex data, this proteomic data, and you want to just get much better analytics in order to save lives.
Perfect. I think that's really exciting personally, that you have not just financial manufacturing applications, but also health applications, which is key at the moment. And so being able to use TabPFN-2.5 for clinical decision making. We're going to jump into some of the questions in the chat. We're not going to have time to cover all of them. So I'll be walking through which are the most relevant ones for Frank, and I'll answer maybe a few quick ones that I've seen. I can answer myself really quickly. So I'll start with a quick question by Marcus before diving into the technical ones. So Marcus Nolka has asked, has TabPFN been applied to demand forecasting spare parts to optimize inventory? Yes. So again, in the report, and just more generally, it's not just healthcare, financial services that Prior Labs is working on, but manufacturing and industrial, with anomaly detection in IoT, predictive maintenance for rotating machinery, semiconductor test optimization. So a lot of different use cases around manufacturing. Then I'll go through a question, I think that was interesting, by Kirti Deshpande, asking a little bit about the accuracy trade-offs that we should expect between TabPFN 2.5 and do you provide distilled lighter models like tree ensembles?
Yes, indeed, we do distill. That is a slide I skipped. That kind of threw me off. So we have. There was a problem that really did plague TabPFN v2 in some applications in sort of e-commerce, etc., where you want to have a fast prediction. If you think about the latency of a standard in context learning transformer, then you can either KV cache, and basically in the model train, do a lot of work, save a large KV cache, and that model.predict, it's just a forward pass with the saved KV cache. But this KV cache actually can grow quite substantially, and therefore actually was off by default, which was also not great for people who wanted to get fast inference time. So you can either use this KV cache in small data applications, it's perfectly fine. But also in large data applications, what you can do is use our proprietary distillation engine. And what that does is it basically takes the fitted TabPFN and then adds an output on top of that. You can think of it as an output head that basically takes a predictive distribution and condenses that into into an MLP or into a tree, etc., and learns to do that over a whole lot of different data sets. And the results of that is, like I showed this plot earlier, where TabPFN in the default was much better than the tree-based methods, tuned or not tuned. And when you have this MLP output, then you do lose a little bit on the performance of TabPFN, but you're still much better than these tree-based methods. And you could distill into an MLP. You could also distill into a tree ensemble. And likewise, a tree ensemble would also outperform the standard trees. This might sound crazy. It's like a different way of fitting a tree. You still have a tree, but yeah, you still have a tree, but you fit it differently. If you have 10,000 data points or 100,000 or a million, your tree is going to overfit. But what the distillation of the TabPFN is going to do, it's really tries to distill this function that TabPFN fits, and you can basically have arbitrary amounts of data for mapping that function. And so you can learn to map that function over many different data sets and then learn to actually output a tree. And that is better than using traditional methods to fit a tree that will optimize your training performance, but will overfit.
Perfect. And that leads us well to a question about the size and the volume of data that we can use. So one of the questions was by Thomas Kopfermüller. What's hindering TabPFN to process larger amounts of data?
Yeah, so I mean, basically, in this version, we still use the same quadratic attention as TabPFN v2. It is only a TabPFN-2.5. It's not TabPFN-3. We chose that naming because it doesn't actually change that much in the architecture. It just does everything better. But the architecture is still, it's a quadratic attention, and so it's quadratic in the context size. The context size is 50,000 data points, 2,000 features. And in order to go beyond that, yeah, different architectures are one way of doing that. So yeah, we're looking at a lot of different ways of scaling up to more data sets, more data points, and there's a lot to come. So stay tuned. But I can already leak that there's a lot of different possibilities. So you can train different architectures that scale better. You can look at retrieval, at fine-tuning, at prompt tuning, at assembling. There's all kinds of approaches. There's our RFPFN that basically, yeah, takes the data set, fits a shallow random forest with leaves that might be 50,000 data points, and then in the data point and in the leaves just has a TabPFN that will scale to billions of data points. So there is no limit per se to using TabPFN for large data. It's just doing it, like having the right combination of all of these different ways of scaling up is going to get you 2 billion data points and also give clear state-of-the-art performance there. And I do think that point is not too far in the future.
Great. We again have a lot of questions, which is great, and you can definitely reach out to Prior Labs and to Frank, our CEO of Prior Labs, afterwards. I'll take one last question, which is on the causal versus predictive, so causal inference versus predictive ML, and so an interesting question by Andrea, which is that TabPFN was trained on causally driven synthetic data. Can its predictions be interpreted causally, or is it still only predictive? Could it bridge predictive ML and causal inference?
Yes, indeed. It does actually help you to make causal statements. So we do have some work going on that can actually read out partial causal structures from TabPFN. Actually, we have a paper about that at the upcoming Tabular AI workshop at Europe's in Copenhagen. And yeah, so basically the short answer is yes, it understands causal structures, even though it's not trained with a loss that tries to optimize for causality, but it's trained on structural causal models, and so it still picks this up. I've also seen a question in the chat on interpretability. So yeah, you can also use SHAP, and yeah, there's a and then you could do SHAP with a distilled version, then this is blindingly fast. So those are clearly, we want this to be super interpretable as well.
Amazing. I think that's a good level of questions. Once again, please do keep in touch, whether it's with Prior Labs directly, Frank, also myself on data science questions, or more widely, Galen Exé. which is one of the leading seed funds in Europe, which invested in Prior Labs at an early stage. So we're really excited to keep in touch on the journey of Prior Labs through the next small releases. And we'll also be having more webinars. So Frank, I'll leave you to say a few final words to the audience before everyone's rest of the Friday.
All right. Yeah, I mean, I don't have that much more to add. I'll answer one question that I still see. Did we also consider column names? Not in this current version, in order to stay comparable, in order to be fair to XGBoost, etc. But stay tuned. There may or may not be a release coming very soon that also looks at that. And yeah, for other things also, stay tuned. Of course, we're looking at everything related to tabular data, time series, multi-table reasoning. We have a lot coming. Causality, we have interventional reasoning. We have this, we actually have a spotlight at NeurIPS about interventional reasoning, where you make predictions, not just to make predictions, but actually to change some variables. And if you don't use causal machine learning, then you have you always have a bias, whether you use gradient boosting or whether you use TabPFN. But with causal TabPFN versus DoPFN, you get rid of this bias and you can just make much better predictions for what variable should you change, for example, for pricing, etc. So there's a lot coming, and yeah, we're keep on accelerating. So super excited about that, and thank you all for being part of the journey.
Thank you. Thanks to the 88 people who joined and for listening through till the end.
All right.